In this discussion, we're going to talk a little bit about the halogenation of alkanes. And this, as it turns out, is a radical reaction. And if we heat or use light with alkanes and halogens, it has to be chlorine or bromine, we will cause a substitution reaction where hydrogen leaves and a halogen replaces that. So that is a substitution reaction. Fluorine's not going to work, too violent reaction, and iodine just too slow to have this take place. Now, when you have multiple sites where this can happen, you're going to get all the different constitutional isomers. So now with the cyclohexane, there is only one kind of hydrogen, and so you could put this bromine anywhere you wanted to, but essentially we're just getting one process here, and we're talking at this stage about monohalogenation. However, if you've got multiple sites, here's a secondary site, here's a primary site, you can get all the different constitutional isomers in that case. Now, if we have a lot of halogen around and not as much alkane, you're going to get multiple sites being halogenated, and you can see that here in figure 15.2. So if you want monohalogenation, you typically use an excess of the alkane, and that allows you to get monohalogenation. In terms of how this happens, okay, so we're in the radical chapter, so we assume that this is going to happen by a radical. Now, the way that we can determine that with some evidence is listed in this table here. And so we need light, heat, and or peroxides necessary for the reaction. Okay, and so again, this allows for the homolytic bond cleavage. O2 inhibits the reaction, and again, in the last discussion, we talked about how O2 can stop radical reactions, and we don't observe rearrangements, which we would observe if we were dealing with a carbocation. And so all three of these points point to a radical mechanism. And so when we deal with radical reactions, there are typically three steps. Initiation, where we start and we form the radicals. Propagation is where we convert things to products. And then termination, again, if two radicals react, we basically kill that radical and we no longer have it able to propagate. Now, to look in terms of halogenation, and you can see the example that we show here with this reaction of cyclopentane with chlorine. If we want to look at this, again, it's a chain mechanism, and propagation, as it turns out, works out to be the most important in these types of reactions. So if we look at this mechanism, again, initiation, we break homolytic bond cleavage to make chlorine radicals. That chlorine radical then will react with cyclopentane and abstract the hydrogen. And again, we're making a new radical. It's a carbon-based radical. This carbon-based radical can then react with another molecule of chlorine to give the chlorocyclopentane product, but it also gives us another chlorine radical. Okay, and that radical can then continue this process. Okay, it can go back to this step here. We also get HCl as a byproduct. Now, in terms of termination, again, any of these radicals could potentially react with each other. Now, this last one here actually forms product, okay? But again, we no longer propagate and we don't create a radical there. But you can also have the two organic radicals come together, forming a different byproduct, or the chlorine radicals can come and form chlorine again. Now, it's important to look at energy changes here because this is going to really determine a difference between chlorination and bromination. And as you can see here, when a chlorine radical reacts here, we break a bond that costs us energy, but we form a new bond. Okay, and that actually gives us energy back, and it's more energy is given back. So this is an exothermic process. When we take this carbon-based radical and react it with chlorine, again, we're breaking a relatively weak bond, that chlorine-chlorine bond, and we are then forming a carbon-chlorine bond, which is stronger. And therefore, this, again, is an exothermic process. And so, again, this is going to cause this to take place pretty rapidly. And this slide here just summarizes that, where we have an exothermic first step and an exothermic second step to give us the halogenated product. Now, we do get a mixture when we're dealing with this chlorination, and we would expect to get 3 times as much primary chloride as we would secondary, and that is because there are more primary carbon hydrogen bonds than there are secondary. There are only 2 CH bonds that are secondary, whereas there are 6 that are primary. And so we would expect a 3-to-1 ratio, but we observe a 1-to-1 ratio. And so this tells us, as it turns out, that the reaction takes place faster on the secondary site, okay? And so here's just a description here. Since the observed ratio is 1-to-1, the secondary carbon hydrogens have to be more reactive so that they form more quickly. And again, you overall get a ratio of 1-to-1. And again, this is just showing in terms of increasing carbon hydrogen bond strength and how that is inversely related to the ease of hydrogen abstraction. It's easier to abstract the secondary hydrogen than it is the primary, therefore it reacts more quickly. And this is, again, what this bullet point says. The statistical grounds don't work here, and that is because of the different energy of reactivity. Now, when we look at chlorination and bromination, same types of stuff happens, the same mechanism takes place, but there are some differences. Chlorination is faster than bromination, so there's a kinetic difference. We would also say that chlorination is unselective. It's going to go after any of the carbon-hydrogen bonds that you've got. However, bromination is more selective. As you can see here, we just talked about this 1-to-1 ratio with chlorination. It's not selective. But if we took the same propane and reacted it with bromine, we would get way more secondary bromine. It's 99% to 1%. And so it's much more selective, but it is slower. We're going to talk a little bit about why that selectivity takes place. It has to do with the energetics. Now, when we deal with bromine here, so just like we talked about with chlorine, we break this bond, okay? Now, the secondary is a little bit weaker, so it's less endothermic there. But either way, this overall radical formation of the carbon radical is going to be an endothermic process, and that's critical. That is very important to why this is a selective process. And the reason for that is because the rate determining step, the slow step, this radical formation step, it's endothermic. Therefore, the transition states are going to resemble the products. Okay, and that's going to cause far more secondary radicals to form, and therefore a much greater propensity for secondary halogenation to take place. And so that is why that product predominates. Now, if we compare that to chlorination, both of these are exothermic, whether it be primary or secondary. Doesn't matter, they are exothermic. Okay, and so in this case, that is a critical difference. Okay, and that the stability of the two radicals is much less important, and that is explained here in this diagram. Now, the rate determining step in this case, exothermic, transition state resembles the starting material. And if you see, the starting material is the same. Therefore, there's not a large difference in this energy of transition state. Therefore, both of the radicals are formed, and we then will also get a relatively equal amount of both halogenated products. And so that's where we're going to stop right now. Just a discussion of halogenation, its mechanism, the difference between chlorination and bromination, and why that is. It's all energy based.